So in the previous lecture, I showed you how we estimate the size of the error. So in other words, for every cell, we would like to know how far is the discrete, the finite element solution away from the exact solution. And we played this from the Galerkin approximation, from the finite element approximation to the interpolation estimate, and from the interpolation estimate to the second derivatives. That was sort of the simplest way to do it, and there are many other ways of doing it. So in one of the following lectures, I'm going to show you, let's say, a posteriori error estimates, for example. But so ultimately what came out of this is that we have for every cell a set of indicators that tells, let's say for every cell we have one indicator that tells us how large is the error, or how big do we believe the error to be. And so the question then becomes, now that I have this, how do I decide which cells I want to refine? So I have 10,000 cells and I have 10,000 indicators, and I need to figure out, well, do I want to refine 50 of these cells or 100 of these cells? And if I want to refine 100 of these cells, which 100 are the ones that I want to refine to get the next mesh on which I can solve again? So this is the purpose of this lecture. This is lecture 17.5. And I want to talk you through the different options that you have in this case, and let's say what are the techniques that we commonly use in our community. So the question in lecture 17.5 is, which cells do you want to refine? And I want to put this into the context of the typical adaptive mesh refinement loop that we always use. So we solve the equation. That's what I've shown you in many of the previous lectures. So you given a mesh, you assemble a linear system, and you solve it. And then in the previous lecture, I showed you how to estimate the error. So that means to compute some kind of refinement indicator on every cell. Then the next step is what we call mark, and that's the purpose of this lecture. So which cells do you want to mark for mesh refinement? And then you actually have to do the refinement, and that involves, let's say, subdividing each cell into its children and possibly refining some adjacent cells as well. So I showed you, for example, the red-green refinement strategy. So these are the four big parts of this loop, and then when you have created a new mesh, you go back to the front and you solve your linear system, or you build your linear system and you solve again there. So for reasons that neither I nor anybody else I know can really tell, in the literature, when you look at papers, you almost always find that this loop is written in uppercase letters. I have no understanding for why this is so, but everybody writes it in uppercase letters. And the best I can come up with is that this comes from the time when everybody was programming in Fortran, and in Fortran, well, people seem to be using uppercase letters for everything. This convention has survived until today, so until 2016, even though the time when Fortran was only uppercase letters is, I don't know, several decades ago. So if you ever wonder why that is so, it's because everybody does it so, because it's always been done that way, always uppercase letters. So, like I said, we've discussed the solve, the estimate, and the refine parts of this loop in previous lectures, and the point of this lecture is then to talk about the mark strategy. So what this mark phase is really, so from the estimate phase you have, you already have a set of refinement indicators. So for every cell K1, K2, K3 until Kn, we have an indicator eta K1, eta K2, eta K3 that tells us something about the size of the error on this particular cell. And the goal of the mark phase is then to decide, based on these indicators, which cells we want to refine. So there are at least three strategies that I can come up with. One would be to mark all cells for refinement. Of course, if you mark all cells for refinement, there wasn't even a need to compute these refinement indicators. But you might have wanted to do this in order to estimate the true error. So maybe you're more interested in the actual size of the error than in using the error indicators for mesh refinement. In that case, it makes sense to compute the error indicators or error estimators. So if you refine all cells, we know from our a priori estimates that the solution will eventually converge. If I keep doing this loop over and over, if I refine globally and I solve again, and I refine globally and I solve again, the error is going to become smaller and smaller and smaller, because we can prove that, for example, for most equations, the energy error is proportional to, let's say, the mesh size h, and that is the biggest, the size, the diameter of the biggest cell. So if I refine the cells over and over and over again, then this h becomes smaller and smaller and smaller, and the error becomes smaller and smaller and smaller. And if the error becomes smaller and smaller and smaller, then clearly the discrete solution UH must come closer and closer and closer to the exact solution. So I know it converges, but it's clearly not an optimal strategy. It requires many more cells than necessary, and if you remember the pictures that I've always showed you where we refine into different areas, then it's clear that I should be able to get much higher accuracy with far fewer cells if I don't refine all of the cells, but only if I refine in those places where something is happening. So strategy 2 takes that into account, and so strategy 2 is typically referred to as bulk refinement or as fixed fraction, and other people use the term Dörfler marking. So the bulk refinement in essence works in the following way. So I have to sort all of these eta k's, for example, from largest to smallest. If I add all of these eta k's up together, then that gives me an estimate of the total error. And what I want to do is I want to mark those cells that together have, for example, 90% of the total error. So let's say if my error indicators are 0.5, 0.2, 0.1, 0.1, then the total error is 0.9. And I would like to refine those cells that together have 90% of, let's say, the total error of 0.9. And of course, I want to refine those cells with the largest error indicator. So I want to, we often phrase this in the following way, I want to find that set of cells that together, for example, account for 90% of the error, but among all of the possible sets that do this, I want to choose the smallest set. So in other words, those cells with the biggest error indicators. So if I use this strategy, then I can sometimes show that that leads to convergence, and not only that, but that in fact it leads to meshes that are optimal in some sense. So you can ask the question, let's say I want to reach a certain level of error. So I want the total error to be no more than, let's say, 0.1. And I know I can achieve this by just globally refining my mesh sufficiently often. But I could also ask the question, so what is the coarsest possible mesh that guarantees that the error is less than 0.1? And so the bulk refinement strategy cannot guarantee that I find that coarsest possible mesh, but it can guarantee that to within a certain factor, the number of cells is, or let's say that the number of cells for the mesh that I construct through the bulk refinement is at most a certain factor larger than the best possible mesh. That's a pretty strong statement, actually. With this bulk refinement, let's say the bulk refinement strategy has typically been used as one of the ingredients of these sort of proofs. It doesn't mean that there are no other refinement strategies that cannot achieve the same goal. But with the bulk refinement, I can actually prove that that is the case. The downsides of this strategy are that oftentimes, let's say if you have a problem where the solution is singular in a corner, so think for example a re-entrant corner in my domain, then the solution is singular in this place and the error is overwhelmingly located only in this one place. So even though maybe you have 10,000 cells, the strategy might refine only a handful of those because they together account for 90% of the error. And so let's say you refine 5 of these cells, you replace these 5 by their 4 children each, so you get 20 cells out of the original 5. So from 10,000, now you have increased the problem size to 10,015. And in essence, what that means is you're going to solve exactly the same problem as before, right? The problem has not become much larger than it was before. And if you keep using this strategy, then you end up with a sequence of meshes that have 10,000, 10,015, 10,025, 10,045, or, you know, roughly equal numbers of cells. And you have to solve the same problem many, many times before you finally get into a range where globally the problem is well resolved. So you're not making much progress towards getting a reasonably fine mesh. And of course, solving each one of these almost the same size problems is going to take roughly equal amounts of time. So if you solve 10 times a problem that has just barely more than 10,000 cells, then that costs you 10 times as much time. So you typically, in cases with singularities, you're not making very much progress. You have to solve similarly sized problems many times. So that can be expensive. So a different strategy is called fixed number. And in essence, what it does is it says, well, maybe I don't care how many, let's say, I don't care what fraction of the total error these cells account for. I'm just going to refine that, let's say, a third of the cells, as an example, or a fixed fraction of the cells that have the largest error indicators. And so a typical strategy would say that in 2D, you should refine 1/3 of the cells with that 1/3 of the cells with the largest refinement indicators, and in 2D, 1/7 of the cells. And I choose these numbers because each one of these 1/3 of the cells is going to give rise to 4 new children, whereas the other 2/3 are going to stay the same. So if you add this up, 4 times 1/3 plus 2/3, you end up with twice as many cells as you had in the previous mesh. And the 1/7 here is defined in the same way. So each one of these 1/7 of the cells is going to give rise to 8 children. So 8/7 plus the original 6/7 of the cells. That also doubles the size of the problem. So every time the problem is going to be twice as big as before. So if I used 1 time unit in the first refinement step, then I need 2 time units, then I need 4 time units. If you add this up, you will find that all of the previous refinement cycles together account for at most as much time as the last refinement cycle. And that means that, let's say, the previous cycles do not dominate the overall amount of time that you take to compute, to solve your problem. So with this strategy, with this fixed number strategy, you end up with something where the size of the problem grows at a more reasonable pace. You don't have this very slow incremental progress. The disadvantage is that you might get meshes that are not optimal, in the sense that you might refine too many cells, and you end up with meshes that are not within a fixed factor away from the optimal mesh. So you're refining too many cells. There's a cost associated with that, obviously. So there's an observation that you can make. So most of the time we refine our cells based on error indicators that might be suggested by strict estimates, or maybe not. Like I told you in the previous lecture, the Kelly estimator is used for all sorts of equations for which it is strictly not true. So we may refine based on heuristically derived error indicators, or we might refine based on strict error estimators, but they overestimate the true error by a factor that we don't know. So as a consequence, in practice, what this mark phase does is it sometimes marks cells that really should not be marked because our error indicators are not accurate enough. And there is a solution to this sort of problem of having refined the wrong cells, is that in each refinement step, we also mark a fairly small fraction of the cells, let's say 5%, for coarsening. So we typically say, for example, we mark the 30% of cells, or 1/3 of the cells that have the largest errors as for refinement, and the 5% of the cells that have the smallest error indicators, we mark them for coarsening. And this is sort of our strategy to undo earlier mistakes. So to give you a little bit of context, in deal.II, the three strategies that I told you about are implemented in the following functions. So the triangulation has a function that is called refine global that takes as argument the number of global refinement steps that you want. And if you want to use the second and third, so the fixed fraction and the fixed number strategy, then there are functions in a namespace called grid refinement, and these functions are called refine and coarsen fixed fraction, refine and coarsen fixed number. So fixed fraction refers to the fraction of the error, and the fixed number refers to a fixed number of cells, which are given again as a fraction of the total number of cells, but not as a fraction of the total error. So each of these three strategies, of course, increases the number of cells and decreases the mesh size, and if the refinement indicators are any good, then all three of these will yield convergence of the error to 0, although possibly at a different rate. So sometimes you need more cells to reach a certain level of error, sometimes you need less, depending on what strategy you choose. And typically with global refinement, that's certainly, I mean, we know it converges to 0, but it leads to the largest number of cells to reach a certain error. So I want to end this lecture by giving you two perspectives, one on time-dependent problems and one on, let's say, a different viewpoint. So for time-dependent equations, typically written with just one s, obviously, so step 26 that I'm going to discuss in lecture 30 is one example. So in those cases, the situation is a little bit different than for, let's say, the Laplace equation that we do in step 6. So for time-dependent problems, what you typically do is you start with a coarse mesh in time step 1. And then you solve time step 1, and of course you don't really know how the solution looks like there, so you refine it a number of times based on refinement indicators, just like we did in step 6, for example, until we have a mesh for time step 1 that we're happy with. And then you do your time iteration. So you, given that you have the solution on time step 1, you compute the solution on time step 2. From time step 2, you go to time step 3, and so on and so forth. And every few time steps, or every time step if you want to, but typically every few time steps, you would adjust the mesh. And so let's say in time step 10, I want a new mesh. What I typically would do is I would start with the mesh from time step 9, and then I would refine and coarsen a few cells on this, because presumably the solution has evolved a little bit, and what used to be an appropriate mesh for time steps 1 through 9 may not be the best possible mesh anymore for time step 10. One of the things that's important in this context is that you cannot simply say, for example, refine 30% of the cells and coarsen 5% of the cells, because that would mean that your mesh in time step 10 is going to be roughly twice as big, or has twice as many cells as what you had in time step 9. And the same thing, of course, will happen in time step 20 and time step 30. So you can't make the mesh finer and finer and finer unless there's a good reason, because the solution becomes, let's say, more and more complicated. But if, let's say, you have a problem where features just propagate through your domain, then what you would like to have is that the number of cells stays roughly constant from each time step to the next, even though you adjust the mesh. And the way you achieve this is that you use this fixed number strategy, but instead of refining a third of the cells and coarsening 5%, you need to do something like, well, I mark a certain number of cells, let's say 5%. So these 5% are going to go away, but they will be replaced by 20% extras of their children. So I'm going to get 1.15 times the number of cells that I had before. But so I need to mark a corresponding number of cells for coarsening, so that if I coarsen these cells away, I get back to roughly a factor of 1 of the number of cells that I had in the previous time step. So I need to make 0.15 times the number of cells go away, and that means that I probably need to mark, let me think about this, I need to mark 20% of the cells to go away, because each one of these cells, let's say each 4 of these cells is replaced by 1 in 2D. So 20% of the cells give rise to 5% of the cells, so I lose 15%. That's exactly the ones that I got from refining 5%. So that's sort of the game you play, and oftentimes it doesn't quite work out that way, but let's say the idea is that you mark proportional numbers of cells for refinement and coarsening in such a way that you roughly keep the number of cells constant. The other thing that I wanted to talk at the end of this lecture on marking is I can give you 2 different perspectives on what adaptive meshes really are. So typically we say we create these sort of meshes by starting with a uniform mesh, for example, the cells that I still have left here, and then I adaptively refine or selectively refine cells in areas where something is happening to make the solution far more accurate. So with a small increase in the number of cells, I'm going to get a significantly larger accuracy in my solution. But there's an alternative interpretation that would say, okay, so I could also see this as follows. So let's say if I had started with a mesh that is always everywhere as fine as these cells here, and then I selectively coarsen away the cells here, for example. So I mean, in reality, I would never, let's say, really start with this sort of mesh, but conceptually I could think of having this mesh that is as fine, and then selectively coarsening away cells in areas where nothing is happening. Then that would mean that I create a mesh that will have roughly the same accuracy as the one that I show you here, but it is far cheaper because it has far fewer cells. So one of these points of view would say, with a small increase in cells, I get far higher accuracy, whereas the other one would say, starting from a very fine mesh, with a large decrease in the number of cells, I get roughly the same accuracy. So one is an argument about the accuracy, and the other one is about cost. And I want to show this to you in a graph. So this is a graph that I created out of data that we published a while ago with a program similar to step 42, which is an elastoplastic contact problem. It's not really important. But what this graph shows is, so the red curve here, that is the error that I get as a function of the number of degrees of freedom. So you can think of this as proportional to the number of cells. That's the error for global refinement. So every time I solve on a uniform mesh, I'm going to refine all of the cells, and I'm going to solve again, and you see that the error goes down by, I don't know, a factor 2 or 4 maybe, who knows. Alternative, of course, would be to do adaptive mesh refinement. And I can say, so for the same number of degrees of freedom on this adaptive mesh, I get roughly, let's say, 30 times smaller error here, right? So this viewpoint would say, if I compare 2 meshes of the same number of cells, then the adaptive mesh produces a far more accurate solution. Now, the other point of view would be to say, well, so for the same accuracy, right? So let's say for an accuracy of 0.001, the adaptive mesh requires only, let's say in this case, so instead of, this is let's say almost 300 million degrees of freedom, whereas on the adaptive mesh I need only, let's say, 3 million. So with a mesh that is cheaper by a factor of 100, I receive the same error. So I just wanted to bring this issue up because it gives us dual viewpoints. So one way to see this would be to say that adaptivity is a way how we can reach a far higher accuracy Whereas the dual viewpoint of this would be to say that with adaptive meshes, I can get the same accuracy with far less cost. And I think depending on what you're interested in, one or the other might be the appropriate viewpoint. So it might depend on whether you have the computational resources, for example, to solve the problem on a uniform mesh. If that was the case, then maybe you're more interested in increasing the accuracy. Whereas in situations like the one that I showed you here, 300 million degrees of freedom, that's a big problem. That requires probably multiple thousand processors to work on this in parallel. So in a case like this, you cannot routinely solve on a uniform mesh. You might not be able to get a better accuracy, but you might be able to solve a problem on an adaptive mesh because that's so much cheaper. So much smaller size, much less compute time for the same level of accuracy. So these are just opposing points of view. There's really no algorithmic difference. It is just, let's say, a different philosophical point of view of what it means to create adaptive meshes. So I hope what you've seen is that there are, let's say, different strategies to mark cells, and they lead to different outcomes. Some of them lead to provably optimal meshes. Others help us refine the mesh in a way that we make significant progress in each step towards, let's say, the mesh that we really want to solve something. That's sort of the point of this lecture. And then in the next lecture, what I'll come back to is, well, are there other strategies to defining these refinement indicators, eta k? In the previous lecture, I showed you how we can define these, let's say, heuristically based on the interpolation error, and that can be, let's say, made rigorous at least for the Laplace equation. And in the next lecture, I'm going to show you how we can define rigorously refinement indicators based on what we call a posteriori error estimates.